All right, so in this video, we're going to start chapter 11, and we're going to move through chapter 11 pretty quickly because a lot of this we've covered in chemistry, but I just wanted to, for those who didn't do AP, I wanted to make sure that they got this information. There we go. So some of the things we're going to look at in this chapter is the first law of thermodynamics, the thermal process, and then the second and third laws of thermodynamics. Okay, so the first law of thermodynamics, you know the law. It's that energy cannot be created or destroyed. It can only change forms, and that's what we've been dealing with this whole course, is how energy changes forms. Okay, so that if that is true, then when heat is added, the energy, the final thermal energy of that process is going to be equal to the initial thermal energy plus whatever heat got added to the system. And then we're just going to rearrange then. And so the change in thermal energy, EF minus EI, is going to equal the amount of heat that gets added. So adding heat increases thermal energy, removing heat decreases thermal energy. So Q will have a positive value when heat is added and a negative value when heat is removed. Okay, so this is just an illustration basically showing how adding or removing heat can do work on a system. So you have a specific amount of energy here, and then if we increase that energy or we add heat, that's going to cause the piston to rise. Whoops. There we go. And so that's going to cause the system to have work done on it. So its final energy is going to be equal to whatever its initial energy was minus the work done. Okay. All right, so here's another equation for the final energy of a system. It's the initial thermal energy minus the amount of work that gets done by lifting or raising that piston up. So delta E, or the change in energy, is equal to negative the work. Okay, so you want to make sure you write down these equations that we've just had for energy, thermal energy, and work. So thermal energy decreases the work done by a system. Thermal energy increases the work done on the system. And there are your key words. Thermal energy can decrease the work done by the system, and it increases the work done on the system. So you also want to make sure you remember this formula. Oh, goodness. There we go. That the change in energy is equal to heat. Change in energy is also equal to negative work. So that leads us to putting all three together. So our change in energy is equal to Q minus the work done. Okay. So this is basically stating the first law of thermodynamics. So this law says that a change in a system's thermal energy is equal to the heat added minus the work done. Okay, so again, you're not creating or destroying energy, you are only having it change its forms, heat and work. So the change in energy is equal to the heat added minus the work done. Heat engines. So an engine is a device that just converts thermal energy into work. That's all it is. And we're not going to go through the examples. Y'all know what a basic heat engine is. And this is kind of the basic gist of what it does. So it takes thermal energy from a hot reservoir into the engine, which does work, okay? And then it converts or changes that thermal energy into exhaust, and exhaust it out into a cold reservoir, okay? So the heat added is QH and the heat exhausted is QC, colder temperature, hotter temperature. So the heat added is equal to the work done plus the heat that's lost to the cold reservoir. So you're always going to lose some heat as waste. That's what's going to the cold reservoir or the exhaust. Okay. So QH is equal to work plus QC. And we can just rearrange that then to find that work is equal to the heat added to the hot reservoir minus the heat released to the cold reservoir. Efficiency. Heat engines are characterized by their efficiency, and no heat engine is 100% efficient. So if you're doing these problems and you get 100% efficiency, you have done something wrong. They will also never be over 100%. So efficiency E of a heat engine is a fraction of the heat supplied to the engine, and that is converted to work. So it's basically the work that's done divided by the heat that's added from the hot reservoir. Another way we can rearrange that is to give us this form, where our efficiency is also equal to 1 minus the ratio of the heat from the cold reservoir divided by the heat from the hot reservoir. And that's just another way to calculate efficiency using just the heat rather than the work. Okay, so suppose an engine is 20% efficient. That means that 20% of that energy, that heat energy, is inputted and converted to work. The rest of it goes to waste as exhaust. Okay, and so that's what it means by being 20% efficient. Okay, so we're going to talk about constant volume processes, and this would be where you're adding thermal energy and it's a thermal process, but you're not changing the volume of that container. So you can increase the pressure, increase the temperature, but you are not changing the volume. The volume is fixed. In those cases, in a constant volume situation, the change in energy, and this is going to be important for you to remember and kind of keep straight. So you might want to take some notes on which one is which. So for a constant volume system, the change in energy is equal to the work, because in a constant volume system, no work is done. Work is equal to 0. Since you are not increasing the volume of the container, then no work is done. Remember at the very beginning, we were taking and adding heat, and that was causing the piston to increase, increasing the volume of the container. Well, in this case, that's not happening. You're not increasing, you're not raising or lowering the piston. There's no change in displacement there, so there is no work that's done, which means the change in energy is just equal to the heat, the thermal energy of the system. And this is just showing you an example of that. Okay. If the gas in the cylinder is heated, and then it expands to do work on the piston, since the pressure of the gas is P and the piston has the area A, the force of the gas is P times A. And work is done, or work is force times distance. So we're looking at a different process now. This is not constant volume. This would be, I believe it's going to be a constant pressure process. Yes. So work done at constant pressure. So again, you're not changing the pressure, you are adding heat, and that is then going to cause work to be done because the piston will raise. The pressure is not going to change, but the piston will raise. And when that piston rises or falls, then you are doing work on the system because you are changing the displacement. And if we look at the formula, that kind of helps us to see that. So the force the gas exerts on the piston is P times the area of the piston, which would be A. And then we're going to remember that work is force times distance. So work done by a gas moving the piston from the initial position to the final position would look like this. And we're just rearranging these things to get to a final equation for work in a constant pressure situation. So in a constant pressure system, the work that's done is equal to the pressure of the gas times the change in volume. Okay.